Everyone, welcome back to another physics webinar. Today's webinar is going to be on reflection and refraction. So we're moving past electromagnetic waves now and moving on to refraction and reflection. So we'll start with a recap of last week's webinar as always, and we're going to talk about the law of reflection, drawing ray diagrams of reflection, exactly how the examiners want you to draw them, absorption and transmission, so two different things that could happen to waves. Then we'll talk about refraction and again drawing the ray diagram, explain why refraction happens, the required practical that goes along with all of this, and then we'll do some exam questions and a quiz if we have time. Okay, so what we looked at last week was radio communications. So what we said was the left hand side of the spectrum of the electromagnetic spectrum, so that's radio waves, microwaves, infrared and visible light, can all be used for communications purposes. So one of them is radio communications. So our mobile phones use radio waves between our mobile phone, phone mouse and satellite, and this type of wave, which carries a signal, is called a carrier wave, and that could be microwaves, radio waves, infrared and visible. Choosing between microwave, radio waves, infrared and visible depends on how much information you have in your signal and the distance needed for the signal to travel. So, in conclusion, the shorter the wavelength, the more information they carry. And this also means that they have a shorter range and they spread out less. But the key fact is that the shorter the wavelength, the more information. And as we know, gamma rays have the shortest wavelength, but out of the ones that are used for communication purposes, visible light has the shortest wavelength. So visible light is therefore able to carry the most amount of information, as opposed to radio waves, which can carry significantly less. Microwaves are used for satellite TV because they can travel in space and spread out less than radio waves. And then we looked at kind of the second half of the electromagnetic spectrum and using a microphone and how does that kind of use X-rays, optical fiber communications, and then we looked at X-rays in medicine, so taking an X-ray, how do we take an X-ray, and talking about this idea of a negative image. So a negative image is basically what an X-ray does, and you point the X-ray tube at the patient and you have a film on the other side which will show the X-ray up. Okay, now it passes through the body, it passes through soft tissue, but it's absorbed by bone, teeth, and metal objects. So the white areas that we see are not actually X-rays hitting the screen. The white areas are where X-rays haven't hit the screen. The black areas are where X-rays have hit the screen. So if you've ever had an X-ray or if you've ever seen an X-ray, you'll notice that you've got white and black areas. The white areas show the bone. And the white areas are not because X-rays have hit the film, they're actually a result of all of the black areas. Okay, so we call it a negative image. And if we want to take an X-ray of a organ, which contains mostly tissue, then we can use a contrast medium that absorbs X-rays easily. Okay, so we fill the organ with this contrast medium. And if we were looking at the stomach, we might use barium in a sort of pill form, which can be swallowed, and that contrast medium is sort of like an ink, which allows us to see inside that organ, because obviously there's no bone, teeth or metal objects in the organ, so we need a different way of showing up black and white areas. Then we looked at radiation dose. So the measure of damage that is actually done is all to do with the radiation dose. So one question that we had last week was what kind of, how many x-rays do you need to kind of suffer, to have damage done to you by the radiation? And we found out that it was actually 2,000 over your lifetime, I think it was. So yeah, hardly any damage done to you if you have an x-ray. Okay, so it all depends on how much the exposure is, what type you use, and the energy per second absorbed by the body. So these 3 points here. Now, alpha causes 10 times more damage for the same time. So we can see that the type of radiation that we use really matters. High doses kill living cells and low doses cause cancer. Okay, so low doses cause cancer, but high doses can kill cancer. This is all to do with X-ray therapy, which can destroy cancerous tumours in the body. So thick plates between X-ray tubes and the body stop X-rays from reaching healthy body tissues, but we really want to zap that tumour and destroy it. So low energy X-rays are what we use for imaging purposes, and high energy X-rays are what we use to kill them off, basically. Okay, so let's talk about reflection and refraction. So reflection is can happen to light waves or sound waves, and it can be reflected at the boundary between two different materials. The law of reflection says that the angle of incidence is equal to the angle of reflection. Okay, so what that means is that the angle that light hits the mirror is the same as the angle when light leaves the mirror. So if a light ray hits a surface at 56 degrees, it will be reflected at 56 degrees. The angle is measured between the light ray and the normal. So let's go through in detail how to draw a ray diagram for reflection. So what I've got here is a standard kind of setup for a ray diagram. And do note that it might be this way round instead, and you might draw your normal here. Okay, so it can be any orientation. So what this pink bit refers to here is our mirror or our reflective surface, but in most cases, it's probably going to be a mirror. The number one first step and the number one top tip that I have for all of you is to draw your normal first. So you've drawn, obviously draw your material and then draw your normal. Okay, so the normal, if we remember, is the imaginary line drawn at 90 degrees to our surface. And it's at a right angle to our surface. Okay, so it should kind of make a cross with your surface. And that's the first thing we draw in. And it's always going to be represented by a dashed line. Next, we have to draw on our rays. Now, when we're drawing on our rays, we obviously know that the law of reflection says that the angle should be the same. So you want them to look like the angles are the same. You don't need to whip out your protractor and start measuring the angles. You can kind of do it by eye and then label them as the same. Okay, so this beam here, does anyone know what this beam on the left is called? What do we call the beam on the left? Put your answers in the chat or the Q&A if you know. What do we call the left beam? Cool. Well done, Santati. It's the incident ray. So we're going to label this one the incident ray. Okay. Now, incident means to be incident on something is to kind of hit it. Okay, is to come upon it, to fall on it. So that's the incident ray. And this one is the reflected ray, because that is the ray that is being reflected off of the surface. So we've got that. And now we label our angles. So the angle is always measured to the normal. Okay, so it's always this angle and not this angle. This is the angle to the surface, or the mirror in this case. We want the angle to the normal, which is why it's so important to draw the normal in, so that we know what angles we're talking about. Now you can label them angle of incidence and angle of reflection, but realistically you're not going to fit that many words into that small angle. So what we do is we label with I and R, and that's it. And that's it, that's you done. Those angles are the same, and the incident ray should have an arrow going in and the reflected ray should have an angle going out. Okay, now there are lots of different things that can happen to waves. They can be reflected, they can be refracted, and they can also be absorbed. What happens to the wave is determined by what type of wave it is, the wavelength, the difference between the two media, and other properties of the wave that will determine what happens to most of the wave energy. So some common examples of absorption are waves hitting the beach and giving their energy to the sand, sunlight landing on a face, which we know will be absorbed, that's why we get tanned or burnt, and sound waves hitting thick materials like curtains, which is why sometimes we can't hear noises outside. Okay. Other things that can happen to waves is they can be transmitted. So to be transmitted is to go from one place to another. That's the definition of transmission. Okay, so some examples of transmission are sea waves passing a shallow area, which continue with their energy mostly unchanged. Light passing through a glass window. Okay, so light comes from outside to inside and continues with 95% of its energy. Ultrasound waves obviously come from the ultrasound scanner, pass through the flesh and scan the baby, but continue with enough energy for the machine to then echo that ultrasound back. And shorter wavelengths transmit better through glass. Okay, so refraction. Actually, has anyone got any questions so far about reflection? Please put them on the chat and the Q&A. You guys know the drill by now. You can obviously interrupt me at any time by putting a question on the chat, but just let me know. Any questions? Okay, so sometimes then light isn't reflected, it's not transmitted, and it's not absorbed. So what else can happen to the light? Well, it can be refracted. So refraction is the change in the direction of a wave when it hits the boundary between two transparent materials. Okay, notice I've put transparent in bold, in caps, and that is because it has to be transparent. Refraction doesn't happen between the table and the chair. Okay, that's not refraction. Refraction must be to do with transparent materials, and that is commonly taken to be air, glass, or water. Okay, so change in the direction of a wave when it hits a boundary between two transparent materials. Now, again, I want to show you guys the ray diagram for refraction. Okay, so here you have the boundary between two materials. Okay, you have the boundary between two materials. We're no longer dealing with just one surface, the mirror. We're dealing with the boundary between two materials. And it's commonly going to be air and then maybe glass or water. Okay, so we'll call it glass for now. I'll just put in brackets. This could also be water. Cool. So, we still have our incident ray. That doesn't change, okay? So our incident ray comes in and it hits our normal. Now, our light is going to bend. So we're going to change the angle. Okay, so this is what refraction looks like. And actually, what I'll do is, to not confuse us, that's going to hit there, and that's going to go down. Okay, so refraction needs to be the bending of the light. So we can't just continue it in a straight line, it needs to be bent. Okay, so let's have a look at our completed ray diagram. We have our incident ray, okay, still called the incident ray. However, the other ray is now called the refracted ray. Makes sense, really. So the angle of incidence is still the same, and the angle of refraction is this angle here. Now, for reflection, the two angles are equal. For refraction, the two angles are not equal. And that's because it's being bent, right? It's being bent. That's not going to be the same angle anymore. If we were to carry it on in a straight line, yes, it would be the same angle, but it's not. Okay, so we don't actually need to know the maths. We don't need to know what the angle of incidence is and how to get the angle of refraction. We don't need to do any maths in it, which is good news. All we need to know is how to draw a really accurate diagram, and that's how you do it. But how did I know that the light was going to bend this way and not this way? Why did the light not bend towards the air? Why did it not bend towards the boundary? How did I know how to do that? Now, this is just something that kind of explains it. So this diagram, I'm sure you've all seen before. When you have a straw in a clear liquid, so lemonade, water, something you can see through, you might see this phenomenon occurring, and it's basically the refraction of light showing up in the glass. So the straw, you can see, seems to go in at this place, but then kind of jumps over here. And this is actually how some magic is done. So it's quite a cool kind of phenomenon, and that all works on refraction. So how do we explain refraction? Well, what we first need to think about is the density of the two materials that we're dealing with. So we already know that we're dealing with two transparent materials. It might be air and glass, might be air and water, might be water and glass. We need to think about the density, and to do this we need to think about solids, liquids and gases. So as we know, we have our three states of matter: solids, liquids and gases. Okay, so in a gas, we obviously know that our particles are spread apart, like so. In a liquid, we got some together, some not, whatever it happens to be. And in a solid, I'm not going to draw it all because that takes too long, but we should know from key stage 3 that all of these particles are nice and closely packed together. So this, we say, is the least dense. Dense basically means how tightly packed are the particles. So least dense, medium dense, a bit more dense, and then the most dense over here. Okay, so most dense over here. Okay, now the density of the material that we're in directly relates to the speed of light through it. So a denser material means a slower wave, because you can think about it as the particles kind of slowing it down. They're more tightly packed, it's less likely to get through. So a denser material means a slower wave. Okay, so glass is denser than water, water is denser than air. So it's this kind of, these levels of density, okay? So from that, we know that light will travel the slowest in glass, okay? It's going to travel the slowest in glass, medium in water, and the quickest in air, which we know it travels 3 times 10 to the 8 meters per second in air. So the denser the medium, the slower the wave. That's the first thing. Now, how I like to remember it is this acronym here, FAST. Some of you may have heard of FAST before, and basically what it stands for is, you know how I said before, how did I know where to draw my line? How did I know that it would go in that direction and not the other direction? This is what tells you, and this is going to help you get the perfect ray diagram every time. So if the wave goes faster in the second material, if it gets faster, so i.e. it goes from glass to air, then it goes away. So these two are linked. Faster and away are linked together. Okay, they're a little pair. Now S and T, as the second two letters, are slower and towards. Okay, so slower and towards are a little pair as well. So it's two pairs, faster away, slower towards. I can't make them two different colours, but hopefully you can kind of see the pairing. So if we get faster, if our speed of light gets faster, i.e. we're going from a more dense to a less dense, the light ray bends away from the normal. If we're getting slower, we go from air to glass, the light ray bends towards the normal. Okay, so let's practice. Let's really try and nail this. So, and the reason why I'm saying let's really try and nail this is actually kind of something that I struggled with at GCSE and even in A level, because no one ever explained to me what away and towards actually means. And so I think it's so important for you guys to understand this. Okay, so let's first of all do the first case scenario. Here's my boundary between my two materials, and I'm going to say that the first one is, let's say, glass, and the second one is air. So it gets faster in the second medium, yeah, because it's going into a less dense medium. Okay, so let's draw our incident ray. That's fine. We're going to draw our instant. Do you know what I've forgotten? To draw the normal. I've told all of you to draw the normal first. So draw the normal, okay, 90 degrees to our boundary, as always. And then draw your incident ray. So let's draw our incident ray. And the incident ray doesn't matter. The direction of the incident ray doesn't matter. I try to draw it at basically 45 degrees, but no one really cares. Then when it goes into air, it gets less dense and therefore it gets faster, okay? There's less particles to slow it down in air, so it gets faster. Then we go to our mnemonic. If it's faster, it's away, okay? Those two match up, faster, away. But what do I mean by away? I mean away from the normal, which means it's going to bend in this direction, and not towards the normal in this direction. But where is that kind of boundary between being away and being towards? Well, if you were to carry on that incident ray, carry it on a bit, what you'll see is that if you were to carry it on, going above it is going away from the normal, and going below it here is going towards the normal. And that's how you know, okay? So this is going away from the normal because it's getting faster, it's going away. Now let's try the second scenario. I'm going to draw my normal and I'm going to draw my boundary. And this time I'm going to have air on the top, and the light ray is going into, let's have water this time. Okay, so the light ray is going from air to water. I'm going to draw my instant ray as normal at 45 degrees or whatever you guys want. I think that's the easiest because it's easier to see where it's going to go. And what you might want to do is carry it on, continue it on, and you can rub this out later. This is what I like to do, just to make it nice and neat. So continue it on, and then you've got to think. So you've got to think. Going from air into water, it gets more dense, yeah? It gets more dense. There's more particles kind of stopping it from getting through nicely. So it gets more dense. If it gets more dense, it gets slower. It gets slower. So let's go to our mnemonic. Slower matches with towards. So our light ray is going to bend towards the normal on this side, not on this side. Okay, this side would be away, this side would be towards. So our light ray, because it gets slower from fast, our mnemonic goes towards the normal. Now we forgot one thing. We didn't do our measuring of our angles. So before I said that the angles need to be measured to the normal, and that's the case here. My I is there and my R for refraction is there. Again, to the normal, I is here and my R is here. Okay. And what you might want to do when you're done is just rub out that continuation of the line, because we don't need that. And that's how to draw the perfect ray diagram. Obviously, you're going to do it with a ruler. No need to use a protractor and measure the angles unless the question says so, but we've never really seen that. But yeah, that's how you do it. Okay, hopefully you guys don't have any questions. I've not seen any appear in the chat. Okay, so showing refraction with wavefronts. What is a wavefront? So wavefront is basically if you were to look at a wave straight on. Okay, so the wave's coming towards you and you look at it straight on. You would basically just see a vertical line, yeah? So imagine you're sat here and the wave is traveling towards you. You're just going to see a straight vertical line. And that's what we call a wavefront. It's the front of a wave. And we can show refraction with wavefronts. It's a different, I think, nicer way of showing refraction. So basically what it is this. So to show wavefronts, you basically just draw a set of parallel lines. Okay, so you can see that this is my light. These are my light waves hitting the boundary between air and glass. The distance between two wavefronts is the wavelength. So the distance between here and here is the wavelength. Okay, lambda that is. So when the wavefronts start to move into the glass, they get slower. And because they get slower, they move closer together and hence their wavelength gets smaller. And this is what causes them to bend towards the normal. Okay, so actually let me draw it here. This is what causes them to bend towards the normal. So as they hit the denser medium, they slow down, they get closer together, and their wavelength gets smaller. This is what is causing them to bend. They're changing wavelength. So as soon as it hits the boundary, you can see that we get this change in direction. Yeah? It's quite fun to draw, actually, I think. So yeah, you get the picture. Now, the way that I like to think of it is a traffic jam. Pretend these little lines are cars. In the second medium, those cars slow down. And in a traffic jam, when all the cars slow down, they get really close together. And that's exactly what happens here. The light rays are slowing down in the second medium, and therefore they get closer together, and therefore their wavelength gets smaller, and therefore that is what causes the bending of light. Okay. Now, the required practical is probably one of the more nasty required practicals. It's cut off the top, but what it says is set up a ray box, slit and lens so that a narrow ray of light is produced. So this is our ray box here. And you're going to put a slit in front of it so that we get a nice beam of light, okay, that we can trace and we can see really nicely instead of it all being all over the place. Then you're going to put your block on an A3 piece of paper and you're going to draw around your block and you're going to draw a normal to the block. So that's depicted by this N here. Then we're going to shine the ray box into the glass block. The angle between the first ray and the normal is the angle of incidence. The angle between the first ray and the normal and the reflected ray is the angle of reflection, and the angle between the normal and the refracted ray is the angle of refraction. So what's happening here is we're not only getting reflection, we're also getting refraction. Some of the light is being reflected, a small amount, and some of it is getting refracted. Okay, so both phenomena can happen in the same experiment, and this is what this experiment is showing. And what you want to do is you're going to vary the angle of incidence by varying where the ray box is in relation to the glass block. And you're going to mark it on each time. So you're going to mark it with an X, mark it with an X, mark it with 2 X's here. And that's the angle of incidence, angle of reflection, and the angle of refraction. And then you're going to mark them with an X and remove the glass block, and you can join them all up when you move the block away. Okay, and what you'll be able to do is measure the angle of incidence, measure the angle of reflection, and measure the angle of refraction, and you'll come up with a table with 3 columns: incidence, reflection, refraction, and you'll be able to see how changing the incidence changes the reflection and therefore the refraction. Finally, then we need to talk about how what happens to water waves. So water waves can also be refracted, and it happens when we go from deep water to shallow water, or shallow water to deep water. So in the diagram, we have, I'm showing you it with wavefronts because I think it's easier. So in the deep water, we've got our wavefronts spaced apart, and then as it hits shallow water, they get closer together. And this is because water waves travel more slowly in shallow water. And vice versa, for shallow water to deep water, they get faster and therefore it refracts. So the water waves are refracting. And you would fill in this diagram by just showing that these start to refract and get closer together. Okay, and that's it. Okay, so that is all of the content for today. I'm going to answer a few questions. Translucent, someone said. No, it has to be transparent, okay? Not translucent, transparent. And then Santati said refraction rays always bend towards the normal line. Not necessarily, they can either bend towards or away, okay, as we saw in the fast mnemonic. Okay, let's go through some of these quickfire questions just to make sure that you've understood. What is the name of a line drawn at 90 degrees to the material? Put your answers in the chat. It's the normal. Good. What term is used to refer to an incoming ray? Incoming ray, the one that hits the surface or the boundary. What do we call that? Incident. Good. What is the law of reflection? Don't feel you need to write it out, guys. Just say A, B, or C. Honestly, it doesn't matter. And that goes for all of them, of course. A, good. So the angle of incidence is equal to the angle of reflection. What is densest? Air, water or glass? A, B or C. What is densest? C, good. Glass is the densest medium out of those three. What happens to light ray when it travels from water into air? Well, it's going from a more dense medium to a less dense medium, which means it's going to speed up. So it goes faster and it bends away from the normal by fast. What word is used to describe a light ray being passed through a material that is transmitted? It goes all the way through. A light ray meets a plane mirror at 60 degrees. What is the angle of reflection? Well, by our law of reflection, the angle of incidence is equal to the angle of reflection. Okay, angle of incidence is equal to the angle of reflection. So that's 60 degrees. A light ray passes from air into water at an angle of 30 degrees. Which of these angles is likely to be the angle of refraction? Well, let's draw it and have a think. So our light ray, so we'll draw up our boundary first, air to water. Okay, so we'll draw our normal just to help us out. And we're going to draw our ray, and that's supposed to be at an angle of 30 degrees. Okay, so that's what they've said. Now, going from air to water, I know you've heard me say this a million times, it gets more dense. If it gets more dense, it goes slower. Slower matches with towards, so it bends towards the normal. Now, if it bends towards the normal, what we see is that this angle is actually much smaller than the incident angle, and so it's likely to be 22 degrees. Okay, so whilst we don't need to know how to calculate the angle, we can definitely say whether it's going to be smaller or bigger. Let me just show you that it's different if I was to do it towards. So if this was to be the other way around, it would obviously bend away from the normal and we'd get it looking like this, in which case the angle would be bigger than 30 degrees. Okay, so it's the opposite way around, and it can all be done by imagining you continuing that incoming ray on. Okay. So this is a table from someone doing an investigation in the refraction of light. Why is light refracted as it crosses from air into glass? Why is light refracted as it crosses from air into glass? Good. Glass is a denser medium. So glass is a denser medium, and therefore light would slow down in it and would be bent, or you can say refracted. Okay, let's do a few more and then we'll do our quiz as promised. So this one is complete the diagram to show the path of the ray of light inside the glass block. So I know this is a semicircle, it doesn't matter. All that we actually care about is the boundary, which is a straight line, so we're good. On top we have our air material, and on the bottom we have glass, as we've been told. So the same drill as always. First we need to check, is it going from more dense going to more dense or going to less dense. So air to glass, it gets more dense, it slows down, we go to fast, slow matches with towards the normal. Okay, and I don't want that to be so big. Towards the normal, so towards the normal would be something like this. Now, what I want to show you really quickly is what happens then when it leaves to go back into air. What would be wrong is for you to carry on that ray out. Because if it's going from glass back into air, it refracts again. So what you need to do is draw another normal at 90 degrees to the boundary, which is hard because it's curved. And you need to do fast again. So it's going from a more dense to a less dense, so it gets faster, so it bends away from the normal, and it would be something like this. Okay, so that would be if the question were to say complete the ray of light inside the glass block and as it leaves the glass block, but luckily we don't have that, so it's just inside the glass block, so we'd be fine just to draw this. But make sure not to extend the ray outside of the glass block because then it refracts again. Okay, so just keep it within the glass block and you'll be fine. Complete the diagram to show the path of ray of light outside the block. So this one is showing it outside of the block. What BBC Bite Size have done, which is where I've taken this question from, is a bit wrong because this bit would have been refracted as well, but we'll ignore that for now. So we've got the glass block going to air, glass to air, more dense to less dense, gets faster, so it bends away from the normal, and we're going to have it going around here. Okay. What I'm going to do is leave these questions on the screen just while I'm talking, and I've got something to let you guys know. So today is going to be the last large group tutorial, so the last tutorial that I'll be running with you guys, which is a bit sad for me, but so yeah, this is the last topic. So if you guys do have any questions, or what I really want to do is, if you guys want to give you some tips for studying, revision, for exam technique, if you guys have any questions for that, how do you handle so many subjects at once, what do I need to do to get a good grade, what about 6 markers, anything like that, please pop them on, submit them anonymously if you want. This is the last session we're going to have together, so it would be really nice if I can help you guys out with some of those kind of more general sort of questions. So if you do think of any, pop them in and I'll try to answer them. Where do we go from here? Well, I do personal one-to-one tutoring on the website, so you can talk to MyTutor and you can have me as a one-to-one tutor, or you can tutor with a tutor like myself. There are lots of other tutors out there as well. So yeah, I also yeah, I just wish you guys the best of luck in your GCSEs when you finally get to do them. But let's do our quiz for now, and if you guys have any questions in the meantime, just pop them on. Okay, so same drill as always. Let's do our last quiz. Joinmyquiz.com 141993. I'll put the link in the chat as always. So you can join from the link on your laptop, computer, iPhone, iPad, phone, tablet. Okay, what sites would you recommend to practice past papers? Let me just answer this while you guys are joining. So I would personally recommend Physics and Maths Tutor. That's the one I use for all of the questions that I bring for us to practice in the sessions. And I personally think it's the best one. It's free, and you know, that there's everything on there, and it's all for the new specification, and it covers all topics. I really think it's the best one that you could use for past papers, and they have exam questions by topic as well. So that's personally what I use. Also, don't forget that you can always go back to any of my tutorials, and you can watch them, and you can pause the video before I kind of answer the question and try them for yourself. So that's another way of doing it. That's probably the one website that I would recommend, Physics and Math Tutor. Will the mini group tutorials still go on? Yeah, small group tutorials are still going on. So if you're in one of my small group tutorials, then we'll still be doing those right up to the end of the 6 weeks. That's not a problem. Okay, I've got 6 of you on, 5 of you on, and there's, how many are there on? 10. Wait for a few more of you to get on if you want to join. Okay, we're going to start then. If you guys want to join halfway through, you can. The link's on the chat. Multiple choice. I think it's about 20, 21 questions. I think you get 30 seconds per question. So, yeah. 71% accuracy, 73. That's really good. Well done, guys. Let's keep it up. .81% accuracy, pushing it right up. Let's see if we can get it even higher. Okay, looks like most of you are done, so let's go through the answers. What do we call the part of a compressional wave that is spread apart? That's rarefaction. Name the type of wave that matter moves at right angles to the direction of the wave. That's transverse waves. Well done, everyone got that right. Light bending as it passes through a raindrop is an example of refraction. Yeah, so I know it looks like reflection, but the light is being bent. Refraction is the bending of a wave disturbance as it passes from one medium into another at a boundary. Which of the following factors contributes to the bending of light? So that's the change in the density of light, okay? And therefore that results in the change of the speed of light, okay? But it all starts because sorry, that should be the change of the speed of light. That's a bit of a rubbish question. Okay, a light ray is incident from water to air. Which of the refracted rays is correct? So you go in to the boundary and go from water to air. So it's going from a more dense to a less dense, so it gets faster, so it bends away from the normal, and that would be D. The ray of light that strikes a reflecting surface is called incident ray. So when it strikes it, when it hits it at the first, it's called the incident ray. The imaginary line perpendicular to a reflecting surface is called the normal. What is occurring? Refraction. So it's that bending of light that we can see in the glass block. How does light behave as it enters these mediums? In every case, it's going from a less dense to a more dense medium. So it gets slower, so it bends towards the normal. So it bends towards the normal. The imaginary line perpendicular to a reflecting surface is called the normal. Bouncing back of a ray of light, sound, or heat when the ray hits the surface that it does not penetrate is reflection. When it bounces back, that's reflection. What does the F in fast stand for? Faster. A stands for away, S stands for slower, and T stands for towards. Okay, so well done. If, oh, a few more, hold on. What does away and towards refer to? That's in relation to the normal. The law of reflection states that the incident angle is equal to the reflected angle, and waves move slower in shallow water. And well done everyone, we got 85% accuracy, and well done to Hi, square root minus 1 is I, and PC, who were top 3. Okay. So that is the end then of today's webinar. As I said, this is the last one, so we won't be going on to anything next week, but what we have done is the entirety of the waves module and covered everything in the GCSE Physics AQA syllabus. So don't forget that when you come to revise for your GCSEs, or just kind of want a refresher on any of the content, then you can access every single one of them on YouTube. So they're all there, and remember that you can kind of go to the tutorials and pause the webinar on the questions. So before I go on to answer them, pause it and have a go at those questions yourself. It's a great resource, and if not, go on to Physics and Maths Tutor for some more practice questions. And yeah, and don't forget that obviously we have one-to-one style tutoring. So if you wanted one-to-one style tutoring with a tutor like myself, then that's something that MyTutor offer. And if you go on to MyTutor, find a tutor, then we'll be able to find you and match you up with a tutor that suits your needs. So yeah, thank you guys for attending the webinars, and I hope you guys have learned lots. Don't forget they're all on YouTube. Bye.